So welcome back. Just some quick messages first. We discussed the timing for the second midterm, and the kind of idea is that we can have the second midterm presented for the week which begins with November the 13th. No, it's November the 14th. The 14th, yeah. So, and we would typically then present it by Thursday the 17th, which means that when we meet then for the exercise session on Friday the 18th, we can start looking at the second midterm. And then we could have as a deadline the weekend after Friday the 25th, which will be our last lecture day. And then the exam week begins with the week of the 1st of December, typically. So we could then decide when it fits best. So take a look at your calendars and just figure out when it fits best to have the deadline. And then for the oral examination, we have the week which begins with December the 19th. And then we, depending on your travel plans and other plans, we can try to have more an individually tailored schedule for the oral examination. Now, so what we did yesterday was to look at diagram rules, and I just wanted quickly to repeat them for you. So the diagram rules which we typically use is to draw topologically distinct diagrams by linking up particle and whole lines with various interaction vertices. And two diagrams can be made topologically equivalent by the formation of fermion lines under the restriction that the ordering of the vertices is not changed. And particle lines and whole lines remain particle and whole lines. Then you, for the explicit evaluation of a diagram, you would sum freely over all the internal indices and label all lines. So today we are going to look at first at some applications. And then we are going to look at a simple model, which we are going to meet again next week as an exercise. But we're going to prepare for a discussion of many-body perturbation theory in terms of Bruyère-Wigner and Rayleigh-Schrödinger. And next week, we need also to discuss the topic of so-called unlinked diagrams and the topic of Pauli violating diagrams, because that is something which becomes important when we move over to copper cluster theory. So when you have labeled all the diagrams, you extract matrix elements for the one-body operators, if that's present. So you will typically have states out and states in. And for the two-body operator, if that's present, with left out, left in, and right in. And then there's a phase factor with a number of whole lines plus number of loops. There's a factor of 1/2 for each equivalent pair of lines. So particle lines or whole lines that begin at the same interaction vertex and end at the same interaction vertex. And then for each interval between successive interactions, you add an energy denominator, which runs like the sum of whole states minus the sum of particle states. And these are basically the rules for setting up diagrams in Rayleigh-Schrödinger perturbation theory. So if you're using Bruyère-Wigner perturbation theory, the energy denominator changes, but all the other things stay the same. So what I'm going to do now is to switch back to a whiteboard, and we're going to look at some examples on calculations of diagrams when we have the diagram, and then we are going to move over to this simpler model here. Did I put on the recording? Yeah, I put on the recording. Yeah, I did. So let's take a look at some examples of implementation of diagram rules. We've seen the second order diagrams. So we basically done all of them for the ground state. Keep in mind now that we are looking at the contributions to the ground state of a system. We are not looking at the what we could call valence space effective interactions, where we're looking at particles outside the core, which then interact with all the particles from the core. That gives us additional types of diagrams. Now we're basically looking at the expectation values and of the ground state of a given system, and we're going to limit ourselves to that type of calculations. So that means typically the lowest state of a given system. So let's look at an example here. So we could have a diagram like this. And then we are going to put vertices on it. So typically you would get an example for a diagram with two body interactions, which looks like this. Now, the way we are going to interpret this diagram is a diagram which now produces, in the intermediate state here, it produces a two-particle, two-hole state here. That's a two-particle, two-hole excitation. Here, on the other hand, if you look at only this term here, you can think of that as a one-particle, one-hole excitation. But the other intermediate state you get, when you look at the different vertices here, this would also be a two-particle, two-hole excitation. So this is a diagram to third order. And this is something which arises from the calculation of the many-body perturbation theory to third order. And what we are going to do now when we use the diagram rules, we are putting arrows on the particle and hole lines, and then we're going to put labels. So we will put a label like an A B here, and a C here. We would have a label I here, a label J, and a label K. Then, when we take the diagram rules, we are now going to sum freely over the intermediate states. So we would have a sum A, B, C, I, J, K. This is also a diagram which you can rewrite in terms of matrix multiplications. So when you calculate these, when you do a computation here, it's not so efficient to actually sum over all the single particle states. You would actually rewrite that in terms of two-body configurations and rewrite every interaction piece as a matrix instead of having four indices. You can store all the four indices, and in the final midterm, we're actually going to practice with many-body perturbation theory. And we are going to look at a simpler model, which is called the pairing model. And for some of you, you may have met that in nuclear physics. And that's a model where we have a constant interaction term. So life is going to be much easier compared to the Hartree-Fock calculation. So what you would have then, if we start from the top interaction here, if we now write down the terms, so we would have whole state to the left going out, I, and a whole state to the left, K going out. There is an interaction matrix element. And then we have an A and C coming in. So that's the top interaction. And now I'm not going to put this subscript anti-symmetrized. So I'm going to assume that the matrix elements are anti-symmetrized. So what I've done is actually I have opened up what's normally called a Hugenholz diagram. And I've opened it up by writing down the vertices, because sometimes if you were to look at the equivalent of this diagram, so let's just write in where we use anti-symmetrized matrix elements, this would look like this. And then we have a whole pair here. And then we would have the same going in and out here. So sometimes it gets a little bit messy when you're putting in labels and arrows and so on and that one. So you would typically open it up. Now, these kind of diagrams, as I mentioned yesterday, when you look into textbooks, it can be a little bit confusing. Like the textbook by Shavit and Bartlett, sometimes they switch between anti-symmetrized and not anti-symmetrized matrix elements. And then you just have to guess from the context what they actually mean. And these diagrams, which you see to the left here, they're typically called Feynman-Goldstone diagram. So this is normally called a Hugenholz diagram. And in that case, we are just sandwiching the interaction vertices, and we deal with the anti-symmetrized matrix elements. These are normally called Feynman Goldstone diagrams. And from the context, it should be clear if we are using anti-symmetrized or not. So here, I'm just assuming that because I think sometimes it's easier to read the diagram when you open it up. And you can open up this many different ways. And if we now put up the mid term here, we would have a whole state J leaving. So that is this guy here is leaving. And we have a whole state K, no, rather a particle state C, which is leaving. And then we have a V. And the next piece is a whole state, a particle state B entering, and a whole state K entering here. You agree with that when we look at the diagrams? And then we would have a term here, which now contains a particle state A leaving, a particle state B leaving, right and left. And then we have the similar for the whole states I and J here. And then we have a denominator multiplied with. So the first term, if we now take the this line here, then we take the sum of the difference between the particle lines and the whole lines. So there will be an epsilon I plus an epsilon J minus an epsilon A minus an epsilon B. And then we take the second one, which is this one. And in that case, we have an epsilon I plus an epsilon J minus an epsilon A minus an epsilon C, sorry, an epsilon C. Then, if we now look at the equivalent lines, equivalent pairs of lines, we see in this case that we don't have equivalent pairs which would begin at the same vertex and end at the same vertex. So there is no factor of 1/2 to some power. Yeah.
Should it be K on the second product?
Oh, sorry, I didn't. Sorry, this is just this should be K. Thanks. This should be an epsilon K. Thanks. Yeah. So if we now look at the number of equivalent pairs, there are no equivalent pairs in this case, so there's no factor of 1/2. This means that actually in total, when you're opening up this type of diagram and you're not taking the anti-symmetrized vertices, there's going to be 1/4. No, will be 1/4, 1/4, and 1/4. There will be 36 diagrams, which will be topological equivalent to the one here when you open them up. Okay, so we also have, in this case, we have the number of whole lines, which are equal to 3, and the number of loops, in this case, which are equal to 3. So that means that this diagram has a plus contribution. Now, there's something which is worth paying attention to. If you now remember the general expression, so this is a diagram which comes from this term here, Mn, and then we have the ground state. We have the interaction matrix elements. We have an intermediate state phi of M, and then we have phi of M, and then we have H of I, phi of N, and then we have the final phi of N of Hi of phi 0. And then we have the denominators here, W0 minus this one, and then we have W0 minus Wn here. So if you now look at the matrix elements which we have ended up with, you remember now that when we looked at the second order diagram, we said that we got a contribution from 2 particle 2 hole excitations for one of the diagrams. So the matrix elements you see here, they would correspond to a 2 particle 2 hole excitation or de-excitation. If you now write the diagram here for that one, this is something which looks like this. So that would be a two-particle, two-hole excitation. So the diagram itself, when you put labels on it, that represents a two-particle, two-hole contraction here. If you look at this one, this is also two particles and two holes. So that means that you have a term like this one. Now, the reason why I'm setting up these diagrams or things in this specific way is because that allows us to interpret the intermediate states. Now, if you look at this case, on the other hand, this is a one particle, one hole excitation because I have a hole here and I have a particle here. So this is an example of a one particle, one hole excitation. And if you write down the diagram, this is a diagram before we perform the contractions in operator form, which looks like this. So this is a one particle, one hole type of excitation. So if we are thinking before we take the contractions, because if you now write out the different vertices which you have here, you can think of them as operators. And then you perform the contractions. So when you're looking at your third order term, what you have in principle, you have three interactions like this. And if we don't put labels on them, we will just have the different legs here, right? If we think of this as operators. And then we start looking at the possible contractions we have. And the way you can think of this now is that you are in some specific state at this point here. And then there is an excitation of the system. And in our specific case, this becomes a two-particle, two-hole excitation. But then one of these links, when we perform the contraction, it links to one of these. These operators do not need to link all of them to that one, because what we saw is that one of the operators links with that one and the other one with that one. So in our specific case, this becomes a one particle, one hole excitation operator. And at the end, we de-excite the system and we get back to the ground state. And then we do a two particle, two hole de-excitation. So the way you can think of this is that there are some complicated interactions of your system at the time t0 here. And when we introduce time-dependent perturbation theory, that is going to give us a nicer way to interpret many of these diagrams from a physical point of view. So if some of you, I know that Håkon, you've taken quantum field theory, and in quantum field theory, you have a specific time order. So then you would have a time t1 and a time t2. And the way you can view this is in terms of different interactions taking place at different times. So you're t0, you're on your ground state, you excite the system. Then there's a new type of excitation, some complicated interactions between the different particles. And then you end up at the final time t2 back to the ground state. So this is one of the ways by which you can read the diagrams. And the power of the diagrammatic interpretation is that you can actually bring in this kind of physical interpretations. So when you look at this diagram, you can think, okay, we do a two particle, two hole excitation. There's an intermediate state, which now becomes a one particle, one hole excitation. And then finally we de-excite and go back to the ground state. So there are many more diagrams. So let's look at another possible second order diagram. So there's another diagram which will appear, which we can label like this. And now we can put in particle lines and hole lines. So we would have a hole line here. We have a hole line here, and one here, and one here. So the way it's written now, we cannot have a hole line coming here and a particle line leaving, because this deals with the contractions which we are doing. So what happens here is that we actually made a contraction between these two guys. And the way we've drawn it now, it's impossible for this to be a particle line. So if we now put on labels, we could label this as an A and B. These are the particle states. This could be an I, J, K, and L. And then we start looking at the different factors which we have to deal with. So we have, in this specific case, we have an equivalent pair of particle lines. We have two equivalent pairs of hole lines. So that means that the number of equivalent pairs here is equal to 3. So that's going to give us a factor of 1 over 2 to the power of 3, which is 1 divided by 8. Then I have 2 loops, and I have 4 hole lines. So that's also going to give us a factor of 1. Then, when I'm setting up the diagram, I'm now going to compute the sum over all the single particle states. So that means I need an I, J, K, L here. And then we can start setting up the matrix elements. So we're going to have 1 divided by 8. And then we have the state I, J here of V. And then we have AB. And then we have in intermediate state here, we have KL and V and then IJ. And this is then multiplied with AB and VKL, like that. So if you now look at the diagrams here, you could rewrite slightly this. So I'm following this kind of slavish manner of thinking in terms of the first interaction vertex, the next one, and so on. So I normally always start at the top. But if you now think of intermediate type of excitations, it would be more appropriate to have this matrix element together with that one. Because that means that you would create a 2-particle state, an intermediate state, A and B. So that would be your intermediate state, which you have here. And then you create also an intermediate hole state, the K and L here, which you have here, which then would actually be the state which you're looking at here. So remember now that again, that here in the general expression, these are many body states. But when we perform the contractions, we end up with matrix elements of a 2-body operator, which then just contain the single particle indices. Because when we take a many-body expectation value between 2 many-body states, or we look at the transition matrix element, and we have a 2-body operator, we can only change at most 2 single particle states. So this is again what we early in the semester labeled as the Condon-Slater diagram, no, matrix element rule. And then we can now look at the intermediate energies which we have to look at. So we would now have an epsilon K plus an epsilon L minus an epsilon A minus an epsilon B. And then for the next one, we would then have an epsilon I plus an epsilon J minus an epsilon A minus an epsilon B. So that's the energy denominator. So we take the whole lines minus the particle lines. And this has a sign plus. So this would be the contribution from that specific state. And you see now that all of these are actually 2-particle, 2-hole excitations or 2-hole states, which gets propagated. So this is just this diagram, which is, this contribution here is just 2-hole states, which change to new 2-hole states. And then we have a 2-particle, 2-hole excitation, which you can then see from this, because this is a 2-particle, 2-hole excitation, and this is a 2-particle, 2-hole excitation. This diagram has a name because you have 4 hole states. So it's normally called a 4-hole, 2-particle diagram. There is another contribution which you will get to third order. Actually, there are many more. If you also take into account the 1-body operator, which we have excluded now. Now we're just looking at the 2-body operator. But we have also diagrams which come from the 1-body operator. So, and the 2-body operator. So we could get diagrams of this type as well, you could have something like this. And many, many other ones. So in this case, we're going to put labels like this, and then we're going to have particle states here. So if we put labels, again, we have I and J, and then we can have A, B, C, and D. And again, if we look at the number of equivalent pairs, if we take this diagram, we have the number of equivalent pairs is now again equal to 3. So that gives us a factor of 1 divided by 8. So we have 2 whole lines, which begin at the same vertex and end at the same vertex. And we have 2 sets of particle lines, which begin and end at the same vertex. We have the number of whole lines, which is equal to 2 here. And then we have the number of loops, which is also equal to 2 here. With that, we can now start setting up the diagram contribution. So in the final midterm, we're actually going to look at many-body perturbation theory, but with a simple interaction. And that interaction, since it's a pairing type of interaction, we are going to look at cases where you don't break a pair. That means that a diagram like the one you see here, it's going to mean that you break a pair, and that will not give a contribution. So the number of diagrams you get simplifies considerably. Sorry. So if we now look up at the final contribution here, we're going to get a plus of 1 over 8. And in this case, we have a sum over ij and a, b, c, d. And we're going to have matrix elements of I and j, v, a, b. And now we can rewrite this as an AB. So now we have a 2-particle intermediate state, CD. And then we have CD of V of IJ here. So this looks very much like the one we had into second order perturbation theory, where we started with a ground state and we ended in a ground state. And we just had a 2-particle intermediate state. And in this case, we get an epsilon I plus an epsilon j minus epsilon a minus epsilon b. And we have an epsilon I plus an epsilon j minus an epsilon c minus an epsilon d here. And in this particular case, what we would label this diagram as is as a 2-hole and 4-particle diagram, or 4-particle 2-hole excitation. That's the way you would think of this. So what you're doing now is actually to bring down the different types of contributions you can get, because these intermediate states, they sum over all possible Slater determinants which you have. And the type of excitations which you can get then are excitations of the type where you have either a 2-particle state, you can have a 1-particle, 1-hole excitation, you can have a 2-hole, etc., etc., etc. So if you look at a diagram to 4-folder, there is a particular case here which is very interesting. So let's now look at a 4-folder term. So let's now put the interaction matrix elements. So it gets more and more complicated. So, but let's now assume that we have, and let's put the dots on the vertices here. So let's do this as a whole line, like that. And then we have this as a whole line. And then we are going to have this guy here is going to be a particle line which comes from this interaction, like that. And this is going to be a particle line which comes from that one, like this. Then we obviously now need to have a particle line or a whole line, but since this is a ground state to ground state contribution, there has to be a particle line. So let me just draw that one in another color. So there would be a particle line which now goes into that state, and similarly into this state. But then, since this is a particle line, and we already have lines entering and leaving the top vertex, this diagram here, or this contribution here, must result in a whole line. Now, if you now look at the intermediate state you have here, this specific intermediate state, if you now count the number of whole lines and the number of particle lines, what this is a four-hole, four-particle excitation. And I leave it to you to put labels and then count the number of equivalent pairs and the number of loops, and then figure out what is the expression for the diagram. But I wanted to mention this because what you will see is that order by order in perturbation theory, you bring in more and more complicated excitations. So when you are at second order, we had only one particle, one hole excitations, and two particle, two hole excitations. To third order, you can actually get three particle, three hole excitations. But to fourth order, you can now generate three particle, three hole excitations, but you could also generate four particle, four hole excitations. But they, in many-body perturbation theory, they contain only the order of the interaction. But as you move on, you bring in more and more complicated excitations. So this is going to be important for the analysis which you're going to make with this pairing model, because then we're going to look at four particles. And then you can actually create four particle, four hole excitations. But when you do many-body perturbation theory to second order, you generate only two particle, two hole excitations. So that means that you will never include these. And if your interaction is strong, then diagrams like this can become important. So, yeah.
How do you count loops in this sort of four-order diagram?
Yeah, so this would actually have two loops actually.
Two loops.
Yeah.
Okay, so then you count the outermost.
Yeah.
And the
I didn't draw it the best way.
Yeah.
Because typically a better way to draw it would be to draw it like this. Like that. And then I would rather put it like this. And then you would have a diagram which goes in like this, and then one like this, and one like that, and one like this. And then you would count this one as one loop.
Which one?
This piece as one loop, and that as a one loop. And in addition, you would have four whole lines. So this is a typical example of a four-particle, four-hole diagram. And the reason why I brought it up is mainly because I wanted you to see how you can build in, order by order, different types of excitations. Now, when we move to our last many-body method, which is going to be copper cluster theory, we can generate these terms by summing a series of interaction matrix elements to infinite order. So we will generate a subclass of diagrams. When you diagonalize, what you're doing when you diagonalize is that you will have, for instance, four particle, four hole excitations to infinite order. So it's actually an interesting case, and you will see that in this second midterm, that when you calculate diagrams like this, you can make a comparison with what you leave out compared with the full diagonalization, because your matrix, which you're going to diagonalize, is going to be a 6x6 matrix. So that's a baby case when it comes to finding all the states. But you will have so let me just say a little bit about the example we are going to look at in the second midterm. So the system which you're going to look at then is going to be a system where we have doubly degenerate single particle states. So that means you can have a spin up and a spin down fermion, a spin up and a spin down fermion. And then we're going to define this as the Fermi level. So this will be the ansatz for the ground state. And we're going to make an assumption here that we are going only to look at Slater determinants where you don't break a pair. So we are going to construct a Hamiltonian which does not break the number of pairs. Yeah, Gianmarco, you seem to have a question.
You mean pairs in the same energy level?
In the same energy level. So this states, this is actually a simple model for what led to the Nobel Prize in superconductivity, where you have a pairing interaction where you only pair terms with opposite spins in the same energy level.
So there are not going to be one particle, one whole states?
No. So this case here,
Okay.
this, if you now draw down the possible ways, if you don't break a pair, you have 2 pairs and you have 4 levels where you can distribute the pairs, right? So that means the combinatorial factor is 4 levels and 2 pairs. So that is going to give you 6. So you will have 6 possible Slater determinants. And you can see that by just drawing here. So you will see that then one type of excitation where you promote 1 pair above the Fermi level is this one. So it's pretty easy. I mean, actually, you don't even need to do the combinatorics here. You can just draw the possible states which you have. So this could now be Slater determinant 1 and so on. And the interaction acts only between pairs. So that gives also a simple Hamiltonian. It's called a pairing Hamiltonian, and it's widely used because you can actually solve analytically this Hamiltonian when you take away the single particle energies, when you make all the single particle energies degenerate. So if you compare this to the Lipkin model, this is actually the Lipkin model tilted. So, and this is also one of these cases where the interacting case gives analytical solutions when you take away the single particle energies. And that has to do with the SU2 symmetry of the system. And then you see you can continue, so you can get, if this is your Fermi level, you can now have a state like this, and this will be your 4-particle 4-hole excitation. So in that midterm, since the matrix here is easy to diagonalize, you can then diagonalize a 6x6 matrix. It's pretty easy. And then you can look at the energy as a function of the strength of the interaction and the spacing between the single particle states. And when you do that, when you diagonalize, you have the exact answer. And then you can clearly then run many-body perturbation theory to second order when you only have 2-particle 2-hole excitation. So that means to second order, you would then be getting contributions of this type, but you will never get this one. So then when you add the contributions to 4th order, you will get a 4-particle 4-hole excitation. And then you can compare that to the exact diagonalization. And the thing you will see is that when you increase the strength of the interaction, then perturbation theory is going to perform worse and worse and worse. Because perturbation theory is actually a Taylor expansion.
When you say 6 possible states
here,
then you mean both 2-particle 2-hole and 4-particle? Yeah, okay.
Everything together. Yep. So the 6 possibilities. So you're going to get the ground state, which is this guy here. You're going to get the 4 of these, and then you have just 1 of these. And it's a model which contains most of the essence of this course actually. And I was thinking that this could also provide a kind of a model for if you want to discuss the this for the final, you can do that. Or if you want an additional challenge, we could look at another physical system where we just provide you with the matrix elements. Now, the thing which is nice with this pairing model is that you're already in a Hartree-Fock basis. So you don't need to do a Hartree-Fock calculation. Okay, let's do a small break here, and then I'm going to present the model which we're going to study next week in the exercises, which is a simpler model, and then we are going to dive into time-dependent many-body perturbation theory. because that's gives us an easier way to discuss the linked diagram theorem. Let's put the recording on pause. So before we switch back to the slides, I wanted to introduce the model which we are going to look at in the next exercise set. And in that exercise set, we are going to calculate diagrams to given orders in perturbation theory. So let me introduce the model so that we have the basic details. And then next week, when we are solving the exercises, we can make links between Breuer-Wigner perturbation theory and Rayleigh-Schrödinger perturbation theory. So we are going to look at the simple two-level model. And this simple two-level model is something which we can find the roots of when we calculate the determinant for the Hamiltonian matrix. And then we have the eigenvalues. We're going to have two eigenvalues. And we'll be interested in the eigenvalue for the lowest line state. And when you then calculate the roots of the determinant, we know that this is just given by the solution of a second-order equation. And we can then make a Taylor expansion of the second-order equation with the square root and everything. And depending on how you do the Taylor expansion, you will be able to obtain Rayleigh-Schrödinger perturbation theory or Breuer-Wigner perturbation theory. So that's a very nice way to look at a diagonalization problem and make a direct link between the two different forms of perturbation theory. And that's it's a useful exercise because it gives us some more insights about what perturbation theory is. So perturbation theory, you can view that as nothing but a Taylor expansion around a specific energy. But the Taylor expansion in terms of the interaction matrix elements. So let's now take a look at this model for the exercise next week. For exercise week 45. And this is a two-level model. And you will recognize many of the elements here. Simple two-level model. And we can look at this as a single particle problem with a particle which can be in two different states. So we're going to label these states as an epsilon 2, and we have an epsilon 1. This is going to be phi 1, which would be the lowest lying state. By assumption here, we just assume now that epsilon 1 is less than epsilon 2. So the state phi 1, when we think of this in terms of the standard way of using annihilation and equation operators, this is going to be an A1 dagger acting on 0. And the state phi 2 is going to be given in second quantization as A2 acting on 0. Alternatively, we can view that one as A2 dagger, A1, acting on phi 1. And we could label this in a slightly different way as 1, 2 here. So this is a particle hole excitation, right? You can, if you now place a Fermi level here, you can now think of putting that there. You could think of this as many body states if you want to. You're not limited to think of this as a one particle state. So it could just be a general two particles, two state system, which could be described by one particle or many particles. So when you do quantum computing, this is actually very relevant because you're often trying to find systems where you have well-identified two levels which can be used as a computational basis. And you could identify one as bit 0 and the other one as bit 1. And they do not need to be single particle states. They can be many body states. So we can leave this a little bit undefined, but here we're going to look at this as a one particle state. Okay. And then we are going to define a Hamiltonian, which now is going to contain an operator H0 plus an interaction piece. And then the H0 is now assumed to be an eigen, to have these as eigen states and eigenvalues. So we have phi of I And H0 is simply now the sum from P equal 1 to 2. And then I have epsilon P of AP dagger AQ, AP, like that. So nothing special here. Huh? And then we make a very simple interaction piece, which has a constant G, and then it has a sum of a PQ, and then it contains only AP and AQ, like that. So we have made simply the assumption here, since these are eigenstates, that H0 of Q is simply equal to delta PQ of epsilon P. Okay, that's the system. Now then, it's easy for us now to calculate the matrix elements. So we know that if we calculate the expectation value of H0 with phi 1, this should simply be equal to epsilon 1, right? If I do the same thing with the state here for the interaction piece, then I would have an A1, and then I have my sum over P and Q multiplied with G, AP dagger, AQ, and then I have A1 dagger of 0. And then you see that the only contraction which we have now, and now we have to, the way I've written it is not in terms of a new vacuum, but this is actually with respect to the old vacuum. And you see now that the only contractions we can make, which are non-zero, would be this one and that one. These are the only non-zero contractions. So that leads to delta P equal to 1 and delta Q equal to 1. So when that means that the sum will reduce, and this gives us simply G. Then we can take the next one. So we would have, if we now take phi 1 with H and phi 2, we can now rewrite this in terms of just phi 1 here. So we can now decide whether we want to use a new vacuum. This is a cross-term matrix element, so H0 is not going to contribute. So we would then have the sum here multiplied with G, P and Q, and then I have my AP, AQ. So we can run these calculations in different ways. And then I would have an A2 dagger, A1, so this is the excitation. And this is then multiplied with phi 1. So I can run the calculation like that, or I can write this alternatively as a 0, A1, and then I can have the sum here over G, PQ, you should get exactly the same, of AQ, and then A2 dagger acting on 0. You're going to see that you get exactly the same type of expressions. So for the first variant, we would have to do the contractions AQ of A2 dagger A1, and then clearly the only contractions which are possible are this one and that contraction here. These are the only possibilities which we have. And you will see that if you take this one, the only contractions when these are now only particle states, actually the same. Okay, so just different ways of doing it with the true vacuum or with the new reference state. And this just gives us G again. So now I have the cross matrix elements, and the only thing which is left now is actually to calculate this one with H and phi 2, and you will find this one to just be equal epsilon 2 plus G. So that means that the Hamiltonian matrix, which we need to diagonalize, and is now given by, so the Hamiltonian matrix is simply equal to epsilon 1 plus G, G, and G, and epsilon 2 plus G. And this is something which is easy to calculate. Now, the thing I wanted to show you then, because we are going to calculate, you can diagonalize it, and then you solve second order equations, and you can then look at the lowest line state, and that's the one you're interested in. And then we can make a Taylor expansion. So one of the things you're going to do in that exercise is to Taylor expand the root, but then looking at the lowest line state. So this is a simple problem. I guess I don't need to set up the determinant here, right? That's almost like offending people, right? So, but if we do many-body perturbation theory, this is an interesting case now. And if we do Rayleigh-Schrödinger perturbation theory, then if we go to first order, this is now given by phi 1 of hi of phi 1. And that's simply given by this term G. Here you can also make nice and interesting comparisons between FCI and the correlation energy, and the correlation energy you get with the perturbation theory. So the reference energy here is obviously given by the exact energy minus omega 0. That's in the perturbation theory. If you do the FCI case, then this is equal to E minus the reference energy, which is then the exact energy minus this epsilon 1 minus G. This is your reference energy. If you do that in perturbation theory, delta E, you want to make the comparison here, then you could rewrite this one as an E minus W0 minus, and then you would now have the, you could define this if you want to make this equal to many-body perturbation theory. No, sorry, to exact diagonalization. This would be the same as E minus omega 0 minus delta E to first order. Then this would be identical to the delta E from FCI theory. So if we now move at the contribution to second order, that is given by the sum over the intermediate states. And in our case now, there's only one intermediate state, and that is this phi 2. So we would have phi 1 of hi, and then we have phi of m, which in our case is just the state phi 2. And then we have an omega 0 minus omega m. Now, omega 0 is equal to epsilon 1. M is just equal to 2 here. That's the specific state. So that means that to many-body perturbation theory, to second order, is given by this matrix element squared, which is equal to G squared, because we calculated, so you would have phi 1 of hi of phi 2. There's only one state, because this is a two-level model, divided by epsilon 1 minus epsilon 2 here. And this becomes simply G squared divided by epsilon 1 minus epsilon 2. So that would be your result to second order. And you will see now that when you set up the diagonalization here, and you get this 2 by 2 matrix to which you have to find the determinant, then if you single out the lowest line state and you make the Taylor expansion, you will see that one of the first terms which pops up is actually a term like this when you do the Taylor expansion. But that's part of the exercise next week. And the you can expand around the exact energy, or you can expand around this energy here. And Rayleigh-Schrödinger perturbation theory is expanding around this energy. And diagrammatically, what this means, if now this H1, which we now wrote as a G of PQ here, and AP dagger, AQ, the way we can now read this one in the diagrammatical sense, if you look at this expression here, so we would have as an operator, you would write this in terms of the two states, P and Q here. And then there is an interaction matrix L. This is an operator representation of that specific operator in a diagrammatic form. So when we now are looking at the contribution we have to second order, what we have then is the initial state, so which we could label as this phi 1. And then we are going to end up in phi 1. And then we have the operator here. And then we have the operator here again. And if we now interpret this as particle and whole states, then we would have a contraction between this guy and a contraction between that guy. So diagrammatically, this becomes equal to a diagram like this. And then the state 2 would be interpreted as a particle state, and state 1 as a state below the Fermi level as this state here. So if you're thinking of this in terms of a Fermi level, it would look like that. If you're not thinking of this in terms of a Fermi level, if you're just referring this to the true vacuum, then you would rewrite this one in terms of a state 1 which comes in and a state 1 which leaves. So without the Fermi vacuum, what you would have then would be a diagram like this. You make the contraction, you have a state 1. You have an intermediate state 2 here, like that. You have a new interaction, and you end in state 1, which in our case is phi 1. And this is phi 1 here. So if this would be the same diagram, if you're not dealing with a new vacuum state, you're just dealing with a true vacuum where everything are particle states. So there are two ways by which you could represent it. And that's why I brought up these two different ways here, because you have you can rephrase everything in terms of the true vacuum. And since you only have one particle, you know, life is much easier because you just have a one creation and annihilation operator. Or you could rephrase it in terms of a new vacuum. But you get, at the end, you get the same expression for the energy, obviously. I mean, this is just a change of basis. And that shouldn't affect the final result. But diagrammatically, the diagrams will look different. Yeah.
Are these the same diagram? When you have the same ingoing outgoing, like previously, we had the whole state, the same guy coming in and out, then you closed.
Yeah. But
going to, I didn't see like the difference.
No, the way you can read this, if you open up this guy here, then if you open it up, so if you break it up here and you bend it up, it goes like that.
Yeah, that's why I thought you said that these diagrams were different.
No, they
are the same.
They are the same.
Yeah, okay.
Oh, yeah.
I thought you said you get the diagrammatic representation.
No, you could say the diagrams look different, but they represent the same physical processes.
Okay.
Because when you look at them, they don't look the same, right? Because you have introduced whole states in a new vacuum.
They tell different stories in some sense.
Yeah. So one is with respect to a new vacuum, but they give exactly the same contributions. So the whole lines, I mean, typically here you would just bend this whole line and have that contracted.
Yeah, but that's just a notation thing.
Yeah,
right?
that's a notation thing.
Yeah. So they just look.
They look different, but they represent the same. So when you break it down to the exact expressions, it's exactly the same. There's only the change of basis which you are implementing here. So when you don't have a new vacuum state, when you have a true vacuum, there are no whole states. And then you have to be a little bit careful with the diagrammatic representation. But they mean the same thing. This is nothing but this expectation value here with in our case, you have only one intermediate state where you have an HI and then phi 2. This is exactly the same, but written out in terms of a particle whole basis or not. And you may meet both types of representations. That's pretty common, especially if you have few particles, because if you have 2 to 3 particles, you would normally skip the introduction of a new vacuum state. But if you're having hundreds of particles, you're just looking at the excitations around the Fermi. So I just wanted to bring this in because in the exercise, you're going to set up diagrams to third order, and you're going to do the Taylor expansion of the second order equation, which results from the Slater determinant for the eigenvalue problem. So that's the next type of exercise. So what I wanted to use the rest of the time is to introduce something which now brings us to the time-dependent formalism. Oops, that connects us also. It's going to connect us with a theory which we are not covering here, which is called Green's function theory. But it's a useful thing to have seen. So let's change to the notes which we have here. And so that should actually come up. Oops, stop share. Why didn't it take that one? There we are. Share. Yeah, it should show that one. Okay, so the let's now take this in a full screen mode. So I'm going to use, I need to introduce an intermediate quantity, which we are going to call different types of pictures. So in quantum mechanics, and you may have met this before, they are called the Schrödinger pictures. They're called the interaction pictures. And then we have the Heisenberg picture. Now, these are also interesting for us because the interaction picture is something which we meet again in time-dependent many-body perturbation theory. The Heisenberg picture leads to the theory of Green's functions. And that's also an interesting way of rewriting the equations. So let me bring up these things. And then if we get time, we will go through what's called the adiabatic hypothesis, which is important for perturbation theory. The adiabatic hypothesis means that we are switching on gradually the interaction. So you could think of a system which at time minus infinity is not interacting. So think of a free electron, and that free electron gets closer and closer to a potential well. And then it gets trapped by this potential well. And then it may interact with other electrons. And then after some time, it gets ejected again, and it's a free electron. So this is one way to think of the adiabatic hypothesis. And that plays an important role when we are looking at the way we understand the interactions, because there may not be in real life what we might call an adiabatic switching. So that's a hypothesis about nature, actually. So the time-dependent Schrödinger equation, or equation of motion, is something you have seen many, many times. And this is the equivalent to you finding a unitary transformation. So what you have here is a unitary transformation as a function of time. I guess this is something you've seen before, right? So you have an operator U, which then is given by the Hamiltonian, and it contains an infinity of repeated interactions, because when you write out the exponential, this gives you just an infinite series of h to the power of something. And this acts on the state at t0. So the next thing is now to move to what's called the interaction picture. And normally what we are doing, and the reason why the interaction picture is so much used in many of these methods, is that we hope or we think that we may have an H0, which is a good approximation to the system, and then that HI takes care of the rest. Now, there's a problem here, however, which we also have to keep in mind, that these two guys do not necessarily commute. So that means that when we do the exponential here, then we run into problems, because if we have the exponential of a sum of these two, we cannot write that as a product of the exponential of H0 and HI. And that leads to this Baker-Campbell-Hausdorff equation, which we looked at. And it leads again to something which is called the Trotter-Suzuki approximation, where you just keep some of the terms in the Baker-Campbell-Hausdorff expansion. And we know that T and V normally don't commute. You can just think of a harmonic oscillator. If you take the harmonic oscillator, the kinetic energy of the harmonic oscillator does not commute with the potential energy, which means that the wave functions are not, which you have from H, are not eigenfunctions of T or eigenfunctions of V, but they are eigenfunctions of H for the harmonic oscillator. So what we define now is another unitary transformation. And this transformation is given in terms of H0. And that acts on the original Schrödinger equation, Schrödinger wave function. So the S here stands for the Schrödinger wave function. So that means that we are finding a unitary transformation which transforms this guy into another representation. And what happens then when we now write it out, you can find the equation of motion if you take the derivative. And when you take the derivative of this equation, what you have then is an equation now where you have taken the derivative respect of t here. So you have minus h0. And then you note also that there is an I and h here, and that knocks out the I here and the h here. And then you have the next term, which now contains this term multiplied with the unitary transformation. So that's, and then you can, if you use the definition of the Schrödinger equation, you can rewrite the last term by just taking minus h0 plus the Hamiltonian here, and then sandwich it in between these two unitary transformations. And by doing that, you find then that you have an expression here. This is the new equation of motion, where now this wave function, the wave function in interaction picture, is then governed by a unitary transformation in terms of h0. So what I did, if you take the previous equation here, if you look at this one, this is now given in terms of this state here. It has this Hamiltonian here. So if you now look at the expression which you see in here, the only thing I did was simply to rewrite that in terms of minus h0 plus h0 plus h of I here. Because this term here is Schrödinger's equation. It has the right-hand side h times this psi of s. So that would be give the h term. And in here, I have just the wave function itself. So I can actually rewrite it like this. It's just a simple manipulation. And then I have a new equation of motion in terms of this quantity here, which I can calculate. And then the order of these operators is actually important because these two guys do not commute. So we have to be a little bit careful. And if we take an expectation value of an arbitrary operator, an interaction picture, we can then rewrite. So this could be any other type of operator. We can always rewrite this in terms of a unitary transformation here. And that means that the operator in the new picture is now given in terms of these unitary transformations here. And this would then be the matrix elements which you need to calculate. And the unitary transformation does not change expectation values as it should. Else we would be in problems. Or there may actually even be a transformation which allows us to become lotto millionaires. That would be fantastic, wouldn't it? And then you can derive the equation of motion of these operators in the interaction picture. And this is also a very important quantity. So that means that this equation of motion now is actually given in terms of the operator interaction picture and the commutator between that one and this H0 here. And this is also a very useful quantity when we are looking at the different types of operators, because if we have this unitary transformation, we can actually calculate other types of operators by that unitary transformation. One reason why I'm bringing this up is also that our next many-body method, which is copper cluster theory, is also going to involve some type of transformations. It's not going to be fully unitary, but it allows us to describe the system which we're looking at in terms of a specific set of transformations. Now, what is common to do then, and I don't know how familiar you are with that, is actually to introduce something which is called the time evolution operator, which is just another way of compactifying your unitary transformation. So I write it like a U here because it's a unitary operation. So what you have now is a series of operations at a time t0, and then you transform into the new state here. And this is normalized so that the t0 is equal to 1. Right, and that should be pretty obvious. So this is nothing but a series of unitary transformations. And this time development operator has some specific properties, which are very important. So it has to be unitary. That means that if I take U emission conjugate times U here, or I take the opposite, it should be equal to the identity matrix. So the operator is unitary, which means that the emission conjugate is equal to the inverse of the operator. And further, when you now apply it at different times, you can actually rewrite this in terms of T over T double prime here. And if you now use this property here, this simply leads to this property which you see here. So these are all properties of a unitary operator here. It means again that when you're looking at these expressions here, you can now, if you now look at the Schrödinger equation in the interaction picture, so what we wrote is actually the Schrödinger equation in the interaction picture, which is this equation which we put here. So this is a new Schrödinger equation. So if you look at that one, you can rewrite it. We have defined this quantity here, so we can rewrite that in terms of the wave function at a time t0. And then we would have the operation of this unitary operator times this other unitary transformation here. And then we can bring this together and we can rewrite it as this term here, where this one now is the definition which we used for the wave function psi of I in the interaction picture. So this is nothing but, if you look at this last term here, this is nothing but us going back to the definition which we had in here. So if I multiply with the exponential of minus I h0t, then I get this wave function. So what I did then, when I have the equation here, is that I simply multiply with e to the minus h0 t0. And then I have the equation in the interaction picture at this specific time. Now, what you see here is then nothing but this operator which we have defined, which allows us to define this operator here. And then it's easy to convince yourself that the properties defined above are satisfied by the definition of U. So it's going to be unitary. The inverse is going to be given by the emission conjugate, and so on and so on. So these are all features which are very useful to remind ourselves of. Then what you can do then is actually to look at, when you look at Schrödinger's equation, you can then find an equation of motion for U. And in that case, what we have then is this differential equation here. And then you can integrate from t0 to a time t by using one of the fundamental theorems of differential calculus here. And then you would then be able, because you know that at t equal t0, then this is just equal to 1. So I can then rewrite this u of t from t0 to t. So this represents in a way the transition operator from a state t0 to state t is a unitary transformation. And I can rewrite it like this. And then this is something which you're also going to see in an exercise next week, a small exercise, where you actually prove that you can rewrite like the third, if you look at the third term here, you can actually rewrite it in terms of these two terms. So we're going to see that next week in one of the exercises. You can, if you now expand this iterative, so what you do then is that you solve these equations iteratively. If you go back here, you can then just start with the first iteration and then you keep putting in terms. And that means that you would get terms of this type here. And this one is something you can rewrite in terms of two terms, where you just change the integration limits. And you can obtain an expression by changing the integration order in the second term via change of the integration variables. And that means that you can rewrite the terms which contain the double integral as a term which has two theta functions. And where the theta function is a standard Heaviside step function. And this step function allows us to give a specific time ordering to the above equation. So that means that the way you will see this is normally written in terms of a time order product, where the time t comes after the time t double prime here. So t is normally then called a time ordering operator. So with a theta function, what happens then is that you have to just simply look at the different time orderings, and then depending on this theta function, this is just going to change according to the values of t prime and t double prime. So you can then rewrite this unitary transformation in terms of this time order product. And this time order product is something you can rewrite then in terms of the exponential of all these terms here. And this above time evolution operator in interaction picture is the one which is used to derive various contributions to many-body perturbation theory. And this is going to be an exercise which is not exercise 26, but another one, because these are slides which I had from a previous variant of the course here. The other interaction the other picture is normally called the Heisenberg picture. And that's extremely useful because we have a way to rewrite the wave function in terms of a new unitary transformation, where I actually take the full Hamiltonian. This is something which leads to the formalism of Green's function theory, which we are not going to look at in this course. So that means that if you combine this equation here with Schrödinger's equation, you would then get this equation of motion here. And meaning that this quantity here is time independent. And that's pretty neat. And an operator in this picture takes this specific form here. And what you end up with then is that the time dependence is then in the operator itself. And this yields in turn the following equation of motion, which ends up with the commutator between the operator and the Hamiltonian. And then if you note that the operator can be related to the corresponding operator interaction picture, you can actually relate these quantities to each other. So the quantity, if you now take this quantity here, you can then replace that one with the unitary transformation with H0. And then you would have the same a relation between an operator in the interaction picture and an operator in the Heisenberg picture. And in the Heisenberg picture, the way you look at the operations here is now in terms of this type of transformation, which in turn implies that this at t equals 0, this is just equal to the Schrödinger operator in the Schrödinger picture is equal to the one in the Heisenberg pictures. And all operators are equal at t equals 0, which is the way it should be. So that means that all these states here are actually the same at t0. And then they're just related to each other by different unitary transformations. So in the Heisenberg picture, you can then construct the wave function from the Schrödinger picture, not from the interaction picture like this. So this is where we're going to stop now. Next week, we are going to look at the adiabatic hypothesis. And then we are also going to look at something which is called the linked diagram theorem. And then on Friday, we are going to most likely move into copper cluster theory, which would be our last many-body method. So since I assume that you had seen these kind of different pictures in one way or the other one, and if you're taking a course in quantum field theory, this expression here is most likely pretty familiar. And there will be
that one.
Yeah.
Okay.
I have a good book explaining this.
Say it again.
I have a good book explaining this.
A whole book.
Yeah, good book.
Yeah.
Yeah.
Which
It's a PDF. It's called Quantum Field Theory for the Gifted Amateur. It's very kind. It's not like testing a show. Gifted amateur.